Greetings and welcome. In today's video we're going to be looking at graphs of polar equations, or some more complicated ones anyway. And we're going to be relating the graph of this function for the regular coordinate plane, the Cartesian coordinate system, and then trying to use those values to plot the points on the polar coordinate system to see what the graph looks like. So our first example we've got is the graph of r equals sine theta, and here I've already graphed the equation of y equals sine theta, or f of x equals sine x, or f of theta equals sine theta, and that's just a regular sine function with a domain or the period occurring between 0 and 2 pi, and the range going between -1 and +1. So let's plot some points from this and see what happens on this plane. So the translation is my y-axis is going to be my theta, or the angle of the point in the polar coordinate system, whereas my y-axis is going to be the r, or kind of the radius of the point, how far out it is at that particular angle. So let's take a look at this. So for 0, 0, alright, so when my angle is 0, the radius is 0. Oh, actually, let me choose a darker color here. So right there. So it starts at the origin. This is going to be pi over 6, or 30 degrees. The value of sine is a half. So at pi over 6, 30 degrees, the value of sine is a half. At pi over 4, it's root 2 over 2, or that's 0.707, I believe. So at pi over 4, I'm going to, let's see if this circle represents 1, at this 45 degree value, 0.7, it's about a little bit bigger than 3/4, something like that, right? Now at pi over 3, that is the square root of 3 over 2, so that's a little bit bigger than 0.8. So at pi over 3 here, it's a little bit bigger than 0.8, something like that. And at pi over 2, or 90 degrees, it's equal to 1. So at pi over 2, 90 degrees, it's equal to 1. So here's the first quadrant of my graph represented here. Okay? So let's continue with the second quadrant here. So this was quadrant 1. Here's quadrant 2's behavior. And we'll look at quadrant 3 and quadrant 4. So for quadrant 2, I'll kind of repeat the same values but in the reverse order, and now I'm going from 1 to 0. So at, let's see, at this angle here, it would be the 0.8. At this angle here, it'd be the 0.707. At this angle here, it would be the half, and then it would come back down to 0. Alright, so far my graph has followed these points, which I assume is going to be a smooth curve, and so let's keep going from here. Now for quadrant 3, my r values are going to be negative. So remember, in the polar coordinate system, so if I'm talking about this angle here and the value is negative, that means to move in the opposite direction, alright, or the opposite ray. So if I'm plotting, actually I'll even pick a different color here. So if I'm plotting this point here, actually let me pick this one here. So it's a half, negative a half, sorry, at this angle here. So negative a half, instead of going in this direction, I'm going backwards, and it's plotting this point, which is one that I already had. Or let's look at this point here, 4 pi over 3 is the 0.8. It's negative 0.8 and change this time. So for 4 pi over 3, that's this angle right here, 4 pi over 3. And negative 0.8 is going to bring me right here. So it turns out that these points happen to be remapping the points from my first quadrant. So it's repeating the cycle around this curve. And then at 3 pi over 2 here, this is at -1. So at 3 pi over 2, I'm going to be going backwards and go up to -1. So you can see, in fact, that it's repeating back on that curve. And then similarly here, these are all negative values. So for quadrant 4, it's repeating those values negatively and is mapping back over each of these points. So in full 2 pi radians for my values of theta, I'll actually do this loop twice. Now you might already have guessed what this curve looks like. It turns out this is going to be a circle. So it's a perfect circle graphed by plotting the points r equals sine theta. So yeah, here's the book doing the same example. They made a table of values and then plotted each point and got the same outcome. Now on my graphing calculator, let's see, let me full screen this actually. If I go to mode, I can go down to polar coordinate system, hit enter on that, and also make sure I'm in radian mode here so I can back out of that. And if I want to graph sine theta, let's actually make a table of this first. So what I can do is go to table set. I'm going to start at 0, and I'm going to count my values by pi over 6, or 30 degrees is what I'm doing. So pi over 6, I'm using radians. Remember I set it into radians earlier, so I have to make sure I'm consistent. So I can hit enter on that, and it's got a decimal approximation of pi over 6. And now if I hit second table, you can see those values. So from 0 to pi, went from 0 to a half to 0.86 to 1 to 0.86 to a half to 0, right? And then if I scroll down here, after pi, it now cycled through those values negatively, and that's when it repeated that loop backwards. All right, and I can actually even, let's see, graph this, and actually this graph is a little bit distorted. Let's see, let's zoom 5. And yeah, that's not actually graphing it properly. I'm not entirely sure what's going on there. It seems to be looping back and forth. Oh, you know what? Let's see. Let me go to window. Theta step. Let me change that to 5 degrees. It might be. Yeah, I think because because it's representing each point with a separate pixel, I think it actually is bouncing back and forth because it's in a function mode where it's kind of drawing a line connecting each of these dots the whole way. I don't know if there's a way I can change that. Yeah, to just dotted mode. Let's see if that works. Yeah, and now there, in fact, you can see that it's a circle, right? So, so there's a way you could do it on the graphing calculator. So I would allow my students to use this to at least make the table of values, and then I think plotting it by hand can be valuable to see the relationship as how it's traveling around this point. Okay, so there's our first example of graphing r equals sine theta, and it's interesting in its outcome. Now let's consider something a little bit more complicated. So here I've got r equals 3 minus 5 times cosine theta. So once again, my y values are going to become my radius, or the magnitude of the point. And my x-axis is going to be theta, or the angle that I'm working at here. So here I've got kind of a translated and stretched cosine function. So its maximum value is 8. So I, in fact, have a maximum value of 8 here. And its minimum value is negative 2. So remember, in the case of that, I'll have some angles kind of bouncing backwards when I represent them. So let's plot our first point. So for 0 degrees, I'm at, or sorry, 0 radians, I guess it's the same thing, I'll be at negative 2. So for 0, I'm at negative 2. So here's this point right there. Let's see, I guess it would have been valuable to have a decimal approximation, so we'll just rough estimate these. So at pi over 4, so pi over 4 is right here, all right, or 45 degrees. It appears as though I'm at roughly negative a half, we'll call it. So negative a half for 45 degrees will be, in fact, right here, roughly. Okay, so far it appears as though I'm decreasing in negative values. I'm approaching 0. So it appears as though my curve is probably doing something like this. Let's see, it crosses 0 somewhere between pi over 4 and pi over 3. So it'll end up crossing 0 at, let's see, this would be pi over 2. Yep. It's at 3. So at pi over 2, all the way up here, it's at 3, right? Pi over 2 is the 90-degree value. And on its way up there, it was increasing. So the radius was increasing, probably something like this. So far I've got this kind of interesting sketch going here. So let's keep going. So at 3 pi over 2, I'm up at 6.5. So 3 pi over 2, once it's all the way over here, here's 5, here's 6, so 6.5, somewhere around there. Let's actually get some angles in between there too. So here's, oh, sorry, that's not 3 pi over 2. My bad. At 3 pi over 4, which is this angle, I'll be at 6.5. So here's 6, so 6.5, somewhere like that. And then at pi, I'm at 8. So pi, I'm a full 8 units. So far it started negative and then it's looped around. And I've had kind of this interesting shape so far, somewhat of a spiral. So let's keep plotting. So now it's going to do these same values and just getting smaller, right? So for quadrant 3 is occurring here, right? Here's quadrant 3. So it's going to be doing the same thing. So let's see. So at this angle, it'll be at the 6.5 again. And then at this angle, it'll be at 3. Right? So 3 right there. And it appears to kind of do this. Well, I guess I'll keep that. It's good enough. And now let's consider quadrant 4's behavior. So it starts off positive and goes to 0 at some point. So it's actually going to be looping like this. So far this curve is very symmetric. And then after it hits 0, it's going to, so for this angle here, let's say, it's negative. All right, and the most negative it gets is at -2. So it'll actually loop around like this and look like that. So I end up having this this little loop inside of a bigger loop. All right, so it's kind of this interesting shape, and the name of this shape is a limacon. So let me write that down. So this is a, and it's actually this weird little C shape. I don't even know how to write that. It looks like that. And so this is called a limacon, is the name of this shape. And another way I could have done this is by making a table of values. So I kind of represented the y values graphically here, but I could have also done it doing this here. So let's see. So I was graphing 3 minus 5 times cosine of theta. And let's see, for table set, I'll start at 0 and go to, not alpha, pi over 6. Hit enter, and let's check out our table again. And notice I did end up getting exactly the same things here. So, right, it went from -2 to 8, and then from 8 all the way back down to -2 in a full 2 pi period. All right. So your text actually would have you kind of do the same thing. Have you kind of calculate these to the nearest tenth. They don't have to be terribly accurate because we're not actually going terribly accurate for this radius value anyway. And if you plot those points in order, you can then kind of draw the smooth curve and go from there. So there are actually all sorts of different shapes that you can get as well. Here's another one. This is called a rose. And then there's actually a variety of different classical curves that you can get here, which actually I'm going to snapshot this and bring this right into my notes. This is a very nice table. And so some of these have different names. I mean, there are some that don't actually even land back on themselves, so there's different variations here. But roses are of this form and have different numbers of petals. Actually, I think tomorrow I'll have, or in the next video, we'll consider the number of petals and the relationship there with some of our variables here. Here's a lemniscate. Man, I'm not very good at pronouncing these. And then here's the limacon that we were talking about earlier. And then cardioid is actually when you have a heart shape. So this one actually comes to a cusp. All right, so it's like kind of a sharp corner. I'll show you an example of that in a moment. And then here, this is actually a smooth kind of a dimple that this shape has here. And then here's kind of another one called the spiral of Archimedes, where r equals a times theta. So it just gets further and further out and just keeps kind of spiraling, so your radius is increasing as your angle increases. So that's kind of an interesting shape there. So let me open up my Geometer Sketchpad. And what I've got here is kind of an example function. So this one's regarding sine. Let's see, okay, don't want to lag out here. And I've got just some sliders controlling some of these different values. So here n is 1, so it's just sine of regular theta. And notice what happens if I change the value of b. It appears as though it's changing the size of kind of my maximum value here. So if I change b all the way up to 3, you can see that it's going up to 3. And b's different values there. I can even do half. B equals 0 isn't very interesting because 0 times the sine would be 0. And then I can do negative 1s and it'll loop it around to the other side. Right? Now, in terms of the rose function, let's see, it was of the form a times sine of n theta, where n is a positive integer. So let me go back to this. So if I have 2 times sine of 1 theta, I have this 1-petaled rose. If I bring that to 2, I get 4 petals. Bring it to 3, I get 3 petals, so kind of an unusual pattern here. And you can see that I actually get a varied number of petals depending on the value of n. So n is affecting the number of petals, where b is affecting the length of each petal. So if b is 3, each petal is 3 long in this case. So let's bring this back down to 1 and b down to, say, 0.5. So now let's consider what happens if I add a constant into this. And here is our cardioid function, where it has a cusp. And then here, you can't see this. This isn't quite circular. It's a little bit flattened off here. And I think I can show you an example of a dimple right there, where it kind of just smoothly transitions. Let's see, let's scroll out. So yeah, you can see kind of I can get a different sized dimple there and different things like that. And actually, so here's another type of limacon, and then I think anytime that the A and B are equal, that's when it will become a cardioid, where it has the cusp there. So that's kind of some interesting outcomes when I add a constant, or if I subtract, I can actually get it to loop back on itself even. So very interesting kinds of curves you can get based off of what we'd have here. And then there's even some other interesting effects I can do. So yeah, wow, all sorts of weird variations. Let's see, let me undo that. There we go. So I can actually have kind of weird distorted, not quite petals on a rose. If these are equal, they will become petals, but I can actually have it go back in slightly and warp out. So there's all sorts of different shapes that we can get based off of graphing functions in a polar coordinate system. So I find this stuff really cool. And let's see, I can even get Patrick's star right there. We'll do some more work with this in the next video, but thank you for watching, and I'll talk to you guys later.